Right, ladies and gents, let's have a little look at our exam paper from 2019. Don't worry that it says foundation. We're going to look at both foundation and higher, and the higher tier people looking at this bit get a nice warm up if you're prepared to watch it, and also some exam tips and tricks that are going to help you for your questions as well later on. Right, let's get started. So, chemistry paper, foundation. First bit nice and straightforward, labelling parts of the I was going to say a cell then, an atom, get it right Dawson. So part A is a nucleus in the middle, part B is an electron going around the outside. Most people are getting that right, don't worry about that. The second bit, which particle has the lowest mass? It's an electron because that's got a mass of almost 0. Again, well answered. Use figure 1 to say which group they're in. So we look at figure 1 and we count there's 1, 2, 3 electrons on the outer shell, which is why we use 3 there for the group it's in. For question 1.4, we want to know the atomic number and the mass number. So the reason the atomic number is 5 is we're looking here, I've got 1, 2, 3, 4, 5 pluses, so that's 5 protons. And I've got 1, 2, 3, 4, 5, 6 neutrons. So a mass number of 11 is from the 5 protons and the 6 neutrons added together. Again, both of these say use figure 1, so we use figure 1. For 1.5, we're looking at bromine, 2 different types of atom with the same, with a different number of neutrons. That should be ringing bells for it being an isotope. For 1.6, this is the first one which throws anyone at some real problems, to be honest. We've got bromine 79 and bromine 81, and the relative atomic mass is 80. So what you need to understand to get this question right is that means that there must be the same amount of 79 and 81 if the average is 80, which means it's this third box here. Okay, moving swiftly on to number 2, because I don't want to bore you too much more than I have to. Right, looking at this, 2 O's, 2 H's, and the 2's go at the bottom, which is why it says bottom multi-choice here. Which type of bonding? Anytime you see these sticks, like you quite often see with alkanes and polymers and things like that, that is a shared pair of electrons, which is covalent bonding. And we reach our next one where people start getting some of these wrong, percentage-wise as a country. Transition metals is the right answer for 2.3, and it's one of the features that we're supposed to know for paper 1 about transition metals. One of their interesting uses they like to ask you about is they form good catalysts, but also that they form coloured compounds. This picture here is really important for 2.4. So if we just scroll down and show you what it is. Which one shows activation energy? Activation energy is B. It's this line here. Now higher tier, they had to draw this onto their graph and they were abysmal at it. Notice how the line goes all the way up to the top and it meets the line there, and it goes all the way down so it's in line with A. Okay, C, just so you know, would be the energy change, which again the higher tier needed to label. Most foundation tier people are good at choosing the letters, it's slightly easier. And then for part, which one shows the energy of hydrogen peroxide? So if we look here, hydrogen peroxide is your reactant, so that's where you're starting off at A, whereas water and oxygen would have been D. Okay, that one people got wrong on the foundation tier, they found it difficult. The clue for question 2.6, energy is being given out to the surroundings, it's exiting, so it's exothermic. And then for 2.7 you get a covalent diagram, which is a little bit nicer than you might get in a higher tier because some of it's done for you already. So there's my shared pair of electrons, and then if I did another shared pair of electrons over on this side, that would be my first mark out of 2, so it'd look like this bit here over in the mark scheme. And then it says over here that oxygen's got 6 electrons. I've used 1 here and 1 there, so I've got 4 left to put in, and anywhere in this circle here, if you put 4 more dots or crosses, you'd get your second mark. Okay? Right. So let's just go through what these diagrams are. There, I've got only one type of thing, that's an element. There, I've got 2 different things joined to make a compound. Here I've got the same compound and another compound as well, so that's a mixture of compounds. Here I've got the same element from A, but I've also got a different element because they're made out of the same type of atom joined together, so that's a mixture of elements. And over here I've got an element and a compound, so it's a mixture of elements and compound. Okay, so that should explain why B is the one with only one compound, why D is the one which is a mixture of elements, and why E has got an element and a compound. 3.4. So chromatography obviously is for separating out dyes and food colourings, which is why we're going for that one. Crystallization is where we made our brink. Our brink. What colour is that supposed to be? Our blue crystals, nice pretty blue crystals. That's a special one there for Chloe because she loved making those. So that would be the copper sulfate solution. If we did want to do this one here, we'd need to do electrolysis, and this one here would be fractional distillation. Okay, it's only 2 lines that you draw, so make sure you don't do any extras. For 3.5, again, some people struggled on this one because you had to draw the diagram. Ideally, you draw it in with the right sort of thing, right sort of scientific 2D style. But if you got Arctic and drew it and labelled it, you still got the marks. So you need a container on the bottom. A beaker or a conical flask is a really good idea. You also needed a filter funnel and a filter paper labelled. And then last of all, you needed to label in the top that the sand would be up there and that the water would be at the bottom. And obviously the sand would be up there because it can't get through the gaps in the filter paper, and the water could. For this next bit about separation techniques, we have water here. It says up here, a student distills salt solution to get pure water. So what temperature would the thermometer go to? Well, what temperature does water boil at? 100 degrees. Bag that and go to the bank, thank you very much. 3.7, describing the process. So if you missed any marks on this one, and people did, it's because you might have think you've already said the key point that you're supposed to have. So the commonly got one is that you said that your solution is heated. That's your first mark. People might forget to mention that the water evaporates. That could be your first lost mark. It's quite easy to say that the condenser makes the water to condense, but a lot of people forget to mention that it cools down the vapour. And then obviously once it's condensed, it runs into the vessel at the bottom, the beaker at the bottom. Okay. Right, rocketing on to number 4, and look at that, ladies and gents, electrolysis. Don't you just love it when that comes up on an exam paper? So higher tier, you got this question in a slightly different format later on, but there were some of the similar problems. Okay, so listen out, look what's going on, and you can still learn from this too if you're still with me. I hope you are. Right, 4.1, 2 variables should keep the same. This is the same as the higher tier, and it was answered dreadfully. Like, people were rubbish at this. Okay, and that's nationally. It's not insulting you or your teachers. You've obviously got an amazing chemistry teacher. You don't get better ones than that. So the big problem that people have is that you're being far too ambiguous, which means you're not being very specific. So if you just said the electrolyte or the copper electrode, you haven't given me enough information. Okay, so what do you need to say? The concentration of the electrolyte. We could accept the volume of the electrolyte or the volume of the solution. You can't accept amount. Okay, get out of the habit of saying amount. When we're looking at the electrodes, you could say the size of the copper electrode or the distance between them. They weren't really commonly talked about. If you're saying that you need to keep the voltage the same, you're misunderstanding the investigation here. You're measuring the voltage, you're not putting an input voltage into it, which should become clear as we go on to the next question. Okay, so 4.2, again back to easier parts of the question here. It's magnesium, zinc, cobalt, because in the size of the numbers is magnesium, zinc, cobalt. A bigger reactivity would be a bigger voltage, which leads us on to 4.3, where people did actually struggle and do a little bit harder, find this a little bit harder. So the voltage would be 0 volts. It does mention figure 7, so let's go back. Copper is used as an electrode in X. Predict the voltage of this cell. So let's go up. There's X. So if we had copper here and copper here, what's the voltage going to be? Nothing, because there's no difference in reactivity between copper and copper. So 0 volts for 1 mark, and then because there's no difference in reactivity for your second mark. Okay? Almost everyone in the country is getting that wrong. It's a difficult one. Okay? For 4.4, how can we get a 12 volt battery using these 1.5 volt cells? So the mark that we're most likely to get, that most people, 3/4 of people would get, how many 1.5s would fit into 12? That's 8. And if you've missed a mark on this, it's because you need to connect them up in series. A little bit of a physics link there. So that's one after another, all together, touching, like you're doing a torch or something like that. 4.5, how would you use a non-rechargeable battery or cell? in an electronic toy because a laptop or a mobile. You don't use them in those because they've got too high of a power demand. You'd be going through batteries like it's no business. Right, and 4.6. Biggest wrong answers to put here is talking about global warming, carbon dioxide emissions and stuff like that, because it doesn't tell you how the hydrogen is generated. So we're looking at advantages and disadvantages of fuel cells. Advantages could be it could be renewable if it's made from like solar or wind or hydroelectric or something like that. It might have that you can travel further or something like that, or that it doesn't produce toxic chemicals. It only produces water is a good example there, because the hydrogen and oxygen reacting together. Higher tier had a more difficult way of getting this question. A disadvantage, maybe the hydrogen is made from non-renewable resources. Maybe it's extracted from hydrocarbons, or maybe it's generated using like electricity from fossil fuels or something like that, or nuclear fuels, which are going to run out one day. Biggest problem there as well could be, its slight tendency to explode, not usually with a cute squeaky pop, but maybe with a death rattling explosion of your car, or even hydrogen pumps, petrol stations not really being a thing yet, which makes a hydrogen car difficult. Oh, would you look at that? We're on question 5 already. We are absolutely rocketing through. Well done on concentrating. So 5.1. What's the missing letter here for the X? Big clue if you didn't get this right. Look up at the top, it says lumps of calcium carbonate. So we've got a solid, liquid, gas or aqueous solution as an option. It's going to be a solid if it's lumps. Okay, now still looking at it just before we go to question 2. Notice that when we've got the products, we've got a solution, a liquid and a gas. So why does it lose mass? It's going to be because the gas escapes. Okay. 5.3, easy maths link here. What's the range? We've got a range here in this table going from 0.47 all the way up to 0.8. There we go, 0.86. All right. When it asks us to calculate the mean, because it's a foundation question, it's very specific, and it says do not include the anomalous result. So if you ignore that instruction and just add them all up and divide them by 4, you can only get one of the 2 marks. Look at the numbers, which one doesn't belong? Oh, that 0.47 is quite different from these other 2. So we're going to ignore that one. We're going to get 0.84, 0.79 and 0.686. Add them up, divide them by 3 and get an answer of 0.83. Okay. People forgot to get rid of the anomalous result on that one, clearly. Here's a graph that's been done by the teacher for you. What type of variable is the mass of the calcium carbonate? So if you have a quick look, now you can get it off the graph, but the easiest one for me is looking at this here. You've added the calcium carbonate and repeated it, and then you've changed here on the graph. You've gone for a different mass of calcium carbonate and a different mass of calcium carbonate. So if it's one that you change, it's your independent variable. You need to know about independent, dependent and control variables. Definitely do it. Number 5.6, as the mass of the calcium carbonate used increases, the decrease of mass of the conical flask and contents increases. You can see that because as this gets bigger, this one also gets bigger. It's looking at the graph. What is the decrease in the mass of the conical flask when a 3G sample, 3 gram sample is used? Now, if you didn't use 3 grams, this is the beauty of the graph because you can find where 3 grams is. So it's not this one, it's this one. We go to 3 grams, we go up, and we go across, and that is above 1, and it's 3 squares up. Handily, that means it's 0.3, so it's 1.3 grams. Okay, 1.30 is also allowed. And we're getting on to question 6, which is the last one where it's just the foundation paper. Okay, they've given you a formula here which you need to do yourself on the higher tier if that's what that's what we're doing. So if you're still with us in the higher tier, you might get a similar question, but just without that little bit of help there. Remember, when we're looking about an efficiency or doing a percentage, it's basically what you got out of what you could have got, times it by 100. So like 6 out of 8 on a test times by 100, 6 divided by 8 times by 100. In this case, the sum that we're looking at using is you've got 184 given out to you, and then you're adding up here the MRs which you've used from here, so that's 232 and 3 lots of the 2, which is 6, and then we're timesing it by 100. So there's your sum. It should come out at 77%, and obviously there's all these decimals, so we're looking at you rounding it. Okay. For question 6.2, again, calculate the mass of aluminium oxide in a 40 kilogram sample. So it's saying it's 38% of that. So the easiest way in my head of doing that is find out what 1% is. So we get our 40, we divide it by 100, we find out what 1% is, and then we can find 38% by timesing it by 38. That's the sum that you'd be looking at there. Your answer should come out at about 15, 15.2 also being acceptable, obviously, depending on how you've worked it out. 6.3, we're looking at calculating the formula mass of aluminium oxide. So we looked at this just the other day, if you're in my class in 2019 looking at this now. So we've got 2 aluminiums, so that's 27 and 27. And we've got 3 oxygens, which is 3 lots of 16. You add all those numbers together and you should get a total of 102. If you write out your workings out and you manage to add them up wrong because you're not using a calculator because I don't know, you just think that's stupid, then you can get your mark for that, but do use your calculator please, ladies and gents. Again, 6.4 percentage yield calculation given to you. They're telling you that they've got a range of numbers up here. You've got to choose which ones that you're going to use. You actually got 28.4 kilograms, and you were expecting that you could have got 31.8. So there's your score on the test. You got 28.4 over here on the right out of 31.8. Times it by 100 to get a percentage. We get a decimal. It does say that you're going to give it to 3 significant figures. 8 is your first significant figure. 9 is your second significant figure. 3 is the third significant figure. Quick check at the number next to it. 0. No, we don't need to round up. You're going to leave it as a 3. Okay, so it's 89.3 for 3 marks. And 6.5. Why is aluminium extracted using electrolysis? This is another one that people found quite difficult to get. So the problem that you've got with aluminium is that it's like all the other ions in that it's very reactive. So it's more reactive than carbon. So first of all, you can't do it. Let's put in the reason why. So carbon can't displace that, or carbon cannot reduce it, are the 2 ones. I'd expect displacement because we like those. We call them like Kim Kanye's, or we start talking about our other famous fit people that we like to think about when we're doing our little analogies. Who we think about here? Channing Tatum's probably going to put a smile on someone's face as we're talking about this. And tell a lie, we've got question 7 here, which is not on the higher tier. Ammonium nitrate dissolves in water. The change is endothermic. What piece of equipment could this be used in? So when do you need something to get cold? It's not a hand warmer. Shut up. It's not a self-heating can. No, can't be that. Sports injury pack. Yes. Put ice on it. Keep it cool. Reduce the swelling. There you go. We'll have that one as our option. Okay. Information here on the steps that they've done. Which thermometer should we use? So we're looking at, the clue is here, we're looking for a resolution or a smallest difference that you can tell between numbers of 0.1. Okay, so if you had this one here between going to 20 and 40, it'd be really difficult to see 0.1 on that. So we're going as far away from that piece of kit as we want. D's got the smallest increments, so we can count up in the ones here, 0.1, 2, 3, 4, 5, 6, 7, 8, 9, and then we go to 21. So that would be by far the best one on there. 7.3, energy is being lost every single time, so it is a systematic error. Let's just run through what these errors are because it's probably something that you're not revising and it is something you need to know. So human errors are mistakes that you're making because you misread that 21 as a 22, or you didn't know the scale was going the wrong way or something like that. A random error are the sort of errors that you get because there's small little inaccuracies all the way through the investigation, and that means that like you get these points plotted on, for example, your graph where they're not perfectly on. That happens all the time. Okay, we just try and reduce those as much as possible. Systematic errors are things that are happening consistently, like in this case the heat escaping through the beaker each time, and a zero error is where the start isn't correct each time. Like for example, if we're looking at spring extension in physics and you count the length that the spring is originally as part of its extension, like the spring isn't stretched normally on its own, or if you have a balance and you don't start it off at 0 grams, if it already reads 0.1 grams and then you start weighing things, all your answers are going to be out by 0.1 grams. So 7.4, again this actually to some extent appears in the higher paper, and people weren't that good at this one. It says a glass beaker was used. Say what you could use to increase the accuracy. Use a polystyrene cup or something like that, anything that would insulate it. It's not about safety, this question. It's not about glass shattering, and loads of top end people put that down. On 7.5, even worse done plotting this and getting it correct. So what we're looking at for this, all 6 points plotted to get you 2 of the marks. A line of best fit, which is going as close to those as close as possible, would get you the 3rd mark. And then a line extrapolated to the y-axis means you just draw that line down, keep it going in that pattern until it hits this axis over here, would be the final one. That would allow you to calculate a starting temperature. So if you did it right, plotted it right, you'd get 20.4. If you made an absolute pig's ear of your plotting and then you drew a line and it met somewhere else, we can count that. You just have to look at your paper. For 7.7, we're looking at 2 things that could cause an anomalous result. So the mixture was not stirred would mean that it might take too long to react, so that some of the heat's lost to the surroundings, so it doesn't reach its peak temperature or something like that. So that's one we're ticking. The temperature of the room increasing, I could understand why you might tick that, but unless you actually did that, then it's not a realistic thing to include down as your anomaly. It's not about thermometers being accurate. A different amount of your reactant being added, your sulfuric acid, that could cause it as an accident. Too much of the potassium hydroxide solution isn't going to be one of our options because we were adding excess of that, weren't we? So because we measured that out perfectly. We measured that out there using 25, you're probably using a pipette or something like that. Okay, it might have been that you could add too much of the sulfuric acid because you're adding that a bit at a time. And we're up to question 8 now. This is where our higher tier paper takes over. The rest of the questions here are identical, so let's just get rid of that